All right, welcome, Julian. We are into chapter 2 right now, and chapter 2 happens to be the longest and the most disturbing chapter, okay? So, by the way I'm going to explain it, you're going to see how simple it is and easy to remember. It's not actually disturbing. All right, chapter 2 is tagged first order differential equation. And this is a broad topic. We are going to discuss 4 major topics under this broad topic. Those are the ones approved anyway for your level. So first, you have the homogeneous DE, you have the non-homogeneous DE, you have the exact DE, and you have Bernoulli's equation. Those are the 4 topics we are going to review as far as this chapter is concerned. So we start with homogeneous. But before we go into homogeneous, what is a first-order differential equation? A first-order differential equation is simply an equation expressed in the form of dy dx, not the square version of it. If it is squared, it becomes second order, right? If it is cubed, it becomes third order. So dy dx plus maybe p of x or p of t, dy dx, p of x, then in bracket y should be equal to q of x, That is a first-order differential equation. And this first-order differential equation can take any form. It can take a homogeneous form. In a broad sense, it can also take a non-homogeneous form. How does it take a homogeneous form? If the value of q of x is equal to 0, then you declare it homogeneous. If it is not equal to 0, maybe it's a value, maybe 5, maybe e of t, maybe sine x, maybe anything at all except 0, then you declare it non-homogeneous, right? Now, in the homogeneous realm, where q of x is equal to 0, you can have a linear homogeneous dE and a non-linear homogeneous dE. You get it? So in the homogeneous realm, you can have the linear version of the homogeneous and the non-linear version of the homogeneous. As for the non-homogeneous dE, you don't talk about linear non-homogeneous or linear homogeneous as the case may be. There's just one broad formula to solve that. So the aspect of being linear is applicable to the homogeneous part. Homogeneous linear and non-homogeneous and non-linear homogeneous, non-linear. So the emphasis here is on linear. So if peradventure that homogeneous dE is a linear homogeneous differential equation, then the best way to approach it is simply solving it by variable separable. Separate the variables x on one direction, y on one direction, integrate both sides, and get your final answer. And do not forget the concept of Pfäffling-Korre. Okay? Do not forget the concept of Pfäffling-Korre because it will help you solve some kind of scrupulous questions when it comes to variable separable. Very, very important. Pfäffling-Korre. Pa stands for partial fraction. Fa stands for factorization. Lin stands for differentiating lin the denominator. And then co has to do with completing the square method. And then re has to do with the remainder theorem. Pfäffling-Korre. Don't forget that. It's very key in variable separable solutions. So once it is linear homogeneous, just apply variable separable and you are good to go. Next, if it is a non-linear homogeneous dE, that is to say, non-linear meaning that the derivative is either raised to a power greater than 1 or the value of the dependent variable is raised to a power greater than 1, which is usually the case. Y there becomes square or cube, as the case may be, or half. And then probably y there happens to be a transcendental function or even a product of the derivative. So when that happens in a homogeneous differential equation, then it is assumed to be a nonlinear homogeneous dE. And now that it is a nonlinear homogeneous dE, there are steps involved in solving those kind of questions. And the very first step there is to first of all check for the degree of homogeneity. The degree of homogeneity is best checked by just looking at the powers of the variables, both dependent and independent. At times, both of them can mesh together. Just calculate their powers. If it is 2, 2, 2, 3, 3, 3, 4, 4, 4, as the case may be, so long as it is uniform, then it is homogeneous. At times, they may just ask you which of the following dEs is homogeneous. Then the top is 2, the bottom is 3. That's the variables, each of them in their terms. And by the time you add them up, and then you take the denominator up and you get -1, automatically the degree is -1. But it is a non-linear. It is a non-linear homogeneous differential equation. Once the degree is greater than 0 or less than 0, you cannot apply the steps. So it must be equal to 0 for you to apply these steps we're about to show you. It must be equal to 0. That means the degree of the numerator and the degree of the denominator must be equal. That means the one attached to the dy and the one attached to the dx must be equal. So that by the time you find their differences by taking the denominator upward, it will give you 0 at the end of the day. So once that happens and you get 0 at the end of the day, the next thing you do is to simply assume you let your y be equal to vx. And then if you differentiate that using product rule, let your dy dx become v plus x dv dx. Substitute these parameters into the equation you have confirmed to have a degree of homogeneity of 0. Once you substitute it into that DE, cancel out the variables. What you're going to cancel out basically will be your values of x. So by the time you cancel out the values of x, you solve by variable separable. So you will be left with x and then v. So you solve them by variable separable. When you're done solving by variable separable, resubstitute the value of v. Remember that y was vx. So if you make v the subject of the formula, v becomes y all over x. Substitute it back and have your final answer by solving by variable separable, as the case may be. Now take note, there are two answers you can get. There's what we call explicit solution and there's what we call implicit solution. If it is an explicit solution, it means that your answer is standing in terms of y only. That means y is on one side, the degree is 1, and there is nothing surrounding it. Y is equal to blah, 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 blah. That is an explicit solution. But if it is an implicit solution, that means your y can stand as square, your y can stand with another parameter of y on one side and x on the other side. That is explicit, right? For example, y plus 1 bracket y minus 1 equal to x squared minus 5. If you stop there, that's actually referred to as implicit. But by the time you make y the subject of the formula, irrespective of the fact that there is y on the other part of the equation, no problem. So long as y is standing on its own, that becomes explicit. So basically, that is how to handle a linear homogeneous and a non-linear homogeneous DA. Linear homogeneous, variable separable. Non-linear homogeneous, check for degree of homogeneity, it must be 0. Substitute y to be vx, substitute dy dx to be v plus x dy dx, solve by variable separable, convert the v to y over x, and boom, you're good to go. So now that takes us to the other part, which is the non-homogeneous DE. Now, what is a non-homogeneous differential equation? A non-homogeneous differential equation is simply an equation whose q of x is equal to whatsoever it can be, except 0. For example, I have p of y divided by p of t plus p of t y equals to q of t, and my q of t can be 5, it can be 2, it can be it can be an exponential parameter of y, it can be anything at all. So long as that q of t is taking a value independent of 0, that makes it a non-homogeneous DE. And once it is non-homogeneous, the best solution you can solve non-homogeneous DE is simply applying what we call integrating factor method. And the law of integrating factor method says that y times the integrating factor is equal to the integral of q of t times the integrating factor dt, where the integrating factor is the exponential of the integral of p of t dt. And by the time you solve that, remember, e raised to power ln x is equal to x, because e raised to power ln something, the ln will get rid of the exponential. You know, if you remember the law that a raised to the power of log b base a raised to the power of log b base a, the base a will cancel the a at the bottom and you're left with b. So that's exactly what we're talking about here. So apply the law of integrating factor when you have a non-homogeneous differential equation. You may be tempted to ask, can we not have a linear non-homogeneous DE? Yes, it is possible. When it is linear, you apply the same principle. When it is non-linear, that becomes a very key question, because here your value of y takes a degree greater than 1. And applying integrating factor may not just be the solution. I think that is where Bernoulli's will come into play. Bernoulli's becomes very important in non-homogeneous linear DE, or let's say non-linear, non-homogeneous DEs. But let's not hypothesize too much into that. Let's go to the next part of this chapter, which is exact differential equation. So looking at exact, for a given differential equation to be declared exact, there are a few things that must be done. Number one, you must first and foremost confirm that the partial derivative of one of the variables with respect to another are equal. The partial derivative of the dependent variable with respect to the independent variable should be equal to the partial derivative of the independent variable with respect to the dependent variable. They must give you the same value for them to be exact. If the two values are not equal, then they are not exact. It can be 0, 0, it can be a factor of 2, something, just anything, but they must be equal at the end of the day for you to declare it exact, right? Good. So at times when you're solving questions on exact, you have to focus your mind on the fact that there are some potential questions that can lead to product rule and can lead to quotient rule, as the case may be. And while differentiating, remember to always keep one parameter constant. And the parameter you are keeping constant is not the parameter at the denominator of your derivative. Remember, the partial derivative of x with respect to y, it means you are focusing on y. Why x there becomes the constant, right? Then the other part, the partial derivative of y with respect to x, means that you are focusing on x while the y is a constant. So just isolate your x, differentiate it properly, and then get your final output. And then, of course, the remaining constant can be a product of it or being differentiated to 0 depending on how it appears. So how do you solve exact differential equations? There are two basic methods to solving exact DEs. The first method is the righteous one. The second method is the unrighteous method. The righteous method will tell you that you first of all have to check for exactness, which is applicable to both righteous and unrighteous method anyway. You have to check for exactness. And then number two, you have to assume that z should be a function of x and y being equal to a. Once you make that assumption, let's assume that the question given to you is x squared dx plus y plus 3 dy. That's in bracket now, y plus 3 dy all equal to 0, right? Good. This is the question given to you. Now, the next thing to do is to find the partial derivative of x with rest of z with respect to x. Equate it to your parameter of dx, which is x squared, and then from there you cross multiply, integrate both sides, and find the value of z. In the process of getting the value of z, your constant is going to be a function of y. A function of y. That is a partial derivative of z that contains both x and y with respect to x. So by the time you do that, you're going to get a function of y. Take note, the x you are picking is the x squared, which is attached to the x. Good. Now the next step is to find the partial derivative of z with respect to y. Now, this is a little bit sensitive. At this point, you first of all have to substitute your value of z, which you got in step 3, into the top of this particular equation. That is a partial derivative of z with respect to y. Substitute that z to be x squared all over x cubed all over 3 plus a function of y. Then look for the partial derivative of that with respect to y. And of course, once you do that, the x will disappear, and then that function of y becomes a prime function of y. And then when you do that, you equate it to the function of y, which is y plus 3. Then integrate both sides. When you integrate a prime function of y, it will give you back a function of y. So you will now get the function of y expressed into a constant, being a or b as the case may be. And once you get this function of y, substitute it back to step 3, which was in terms of z, where you have function of y, substitute the value you have there, and boom, you are good to go. Multiply all through if necessary to get rid of the fractions, and then that is just that. Good. So that is how to solve it in a righteous way. But if you want to follow the unrighteous method, which happens to be the simplest way and fastest way I usually teach students, then all you need to do is to simply write down your equation, having confirmed that it is exact. The dx, which is the independent variable, is always the major. The dy, which is the dependent variable, is always the minor. Once you make that assumption, the next thing is on the dependent variable, or let me start with the independent variable, y is a constant, while on the dependent variable, x is equal to 0. So anywhere you see y in the dx part, declare that y to be a constant and focus only on the x. Anywhere you see x on the dy part, declare that x to be 0. Substitute it to be 0 immediately. Solve it. Whatsoever you get at the end of the day, integrate both sides. And that gives you the final answer. I hope I'm clear. So let's take a typical example. I have x cubed dx plus y plus 3, all in bracket, dy equal to 0. The major, of course, is the x cubed, right? Because it is attached to the x. You always have to separate it like that, just in case they don't put it in that order. Then the minor is y plus 3 dy, isn't it? Good. So at the major, your y is the constant, while you focus on the x if there is any x there. But if there is no x there, integrate a constant, if you integrate 0, you get a constant. Then, as for the other part, which is the dy, remember, x is equal to 0. By the time you rationalize that, integrate both sides and sum up the final answer, and you're good to go. So that is that for exact DE. So now that takes us to the last part of this chapter that happens to be the longest chapter. And that last part is Bernoulli's equation. Yeah, that one comes up, Bernoulli's DE. Now, according to Sir J. Bernoulli in 1695, that's quite long, bro. That's quite long. Ancient of days, as old as you are. So according to Sir J. Bernoulli in 1695, the standard form of a non-linear DE is in the form dy dx plus p of xy being equals to q of xy raised to power n. I take it again. Dy dx plus p of xy equals to q of xy raised to power n. The only difference here is the addition of y raised to power n after the q of x, just like it is in the standard form of a first order differential equation. Just add y raised to power n at the top. That makes it a Bernoulli standard form of equation. And the fact there is, if that n happens to be equal to 1 or 0, then automatically the above becomes a non-linear DE. Yes, it becomes non-linear. Why do we say becomes non-linear? Simply because, where n is equal to 1 or 0, okay, fine. N can be equal to 1 or 0. Take note. If, however, n happens to be 0, it becomes a linear DE, right? Good. But if n happens to be 1, then at that point, it will no longer become a linear DE. You can always confirm that. However, but as far as this mathematics is concerned, the above nonlinear DE can be converted to a linear differential equation using 4 steps, 4 basic steps. Or let me just call it 5 steps because they are 5 in number actually. 5 steps to convert it. It's already nonlinear. Why is it nonlinear? Because of the presence of y raised to power n. That value of n is always greater than 1, and it can also be less than 1 as the case may be. If it is 0 or 1, then it becomes linear. But in this case, it is not 0, it is not 1, so it's greater or less than. So it's automatically a non-linear DE. So the 4 steps in solving are: number 1, divide the DE by y raised to power n. Divide all through. And once you do that, you have y raised to power minus n dy dx plus p of x y raised to power 1 minus n being equals to q of x. Step 2, multiply the DE by 1 minus n. The 1 minus n is the power of the y after the p of x. divide all through by that, and you have 1 minus n in bracket y raised to power minus n dy dx plus 1 minus n p of x y raised to power 1 minus n being equal to 1 minus n in bracket q of x. That's step 2. Then step 3, assume z to be equal to y raised to power 1 minus n and differentiate. So if you let z to be equal to y raised to power 1 minus n, differentiate that with respect to x. I emphasize it. You are differentiating that with respect to x. So you're going to have 1 minus n in bracket y raised to power 1 minus n minus 1 times dy dx, which at the end of the day is going to give you 1 minus n in bracket y raised to power minus n dy dx, which is just the initial of step 2. And then you can substitute, which is step 3. Substitute z to be y raised to power 1 minus n. That will now take the position after the p of x, and then substitute dz dx to be 1 minus n y raised to power minus n dy dx, which will take the position of the first part of the dE. And at that point, step 5, you now obtain a linear differential equation. So, but in most cases, once you get to step 3, just assume the gargantuan write-up you have there as dz dx, and assume your y raised to power whatsoever that is there as z, and then just move on. Automatically becomes linear. So once it takes the form of linearity, pick your p of x, pick your q of x, find your integrating factor. And of course, your integrating factor still remains the exponential of e raised of the integral of p of t dt. And whatsoever you get, you now substitute in the formula, which is z, the integral of the integrating factor, being equal to the integral of q of x times the integrating factor. The q of x we're talking about now is the one at stage 4, right? Very important. So always remember at the end of the day to convert your z to the y raised to power minus 1 minus n, as the case may be. So you must take it back to the initial format. Your answer is not expected to be in the form of z because it wasn't given to you in the form of z. And boom, you're good to go. So you can answer as many questions as possible. You can find them in your textbook. All right, thank you for listening. This is the end of this so-called chapter 2 that is so disturbing. We'll meet again in chapter 3. Boom.